Okay. So let's explore DGPS and kinematic positioning mode in rtklib. So okay, uh, in both DGPS and kinematic mode, there would be a base and a rover mechanism. The GNSS receiver, uh, which is here, acts as a base station, and another GNSS receiver where is somewhere else will act as a rover stations. So they will form a baseline, and the position of a rover station is determined relative to a base station. So what we will do in rtklib is we will use data of base station and rover station of the same time period to perform either a DGPS or kinematic positioning mode. But there is a difference between a DGPS and a kinematic positioning mode. In rtklib, the DGPS positioning mode only use pseudo range data or code phase observation data, while the kinematic positioning mode use both code phase and courier phase observation data. So the solution from kinematic positioning mode is more accurate than obtained from DGPS. Okay, there would be base and rover for both DGPS and kinematic positioning mode, and the distance between base and rover, which we call a baseline. For a short baseline, both DGNSS and uh, kinematic positioning mode remove the errors from satellite and atmosphere, along with satellite orbit error, clock error, relativity error, ionosphere error, and troposphere error. The assumption is that for a short baseline, there would be there would be a same atmosphere conditions, so the errors from ionosphere and troposphere would cancel. And since both base and rover stations observe the same satellite, so that the error from satellite orbit, clock, and relativity would cancel out in a DGPS and kinematic positioning mode. Okay, let's perform DGPS positioning mode in rtklib. So first, let's set settings for DGPS. Let's choose DGPS positioning mode. Okay, both frequency will be used. 15-degree elevation mask, the receiver dynamics off, earth correction is off, ionosphere correction is set to off, troposphere correction is set to off, and satellite ephemeris is set to broadcast. Okay, these are parameters in setting 1. Setting 2 will leave. Setting 2 will leave output stats position, and in a position tab we will have to supply a coordinate of a base station. So here are several options. We will choose derive base station coordinate, which is the Rhinix header position, and Okay, the settings for DGPS is done. Now let's supply rover observation data. We will use WT21 as a rover. Let's apply base station observation data. We will use WTZZ as a base station data, and let's apply a navigation data. This is of WTZZ, and uh, the solution is solution will be stored in the same directory. Let's execute DGPS. Okay, the position file is this. Q equals to 4 means positioning mode is a DGPS. Let's close this and let's view the plot. Okay, this is the plot. Variation in east west, north south, and up down component. The precision obtained is 18 centimeter in east west, 27 centimeter in north south, and 48 centimeter in up down components. Okay, we can see the fluctuations of a solution, but the fluctuation range is confined to 1 meter, from minus 0.5 meter to 0.5 meter, and the average precision or accuracy obtained is 18 centimeter. Okay, and this is better than precision obtained in single point positioning. Okay, this is the result after DGPS positioning mode.